Okay. So yeah, Jingtao is very important for this, what I'm going to show. And then, of course, I also acknowledge funding for different sources. Okay, so the motivation for this is really the downscaling of electronics. And heating is a very important problem there. And of course, heat transport, getting rid of the dual heating. But if you scale down to basically down to the molecular scale, this becomes an even bigger problem because you are concentrating the energy very much. And we'd like to describe what goes on here from a physics point of view. So of course we like to look at the joule heating, but I'm also going to focus a lot on current-induced forces on the atoms, how the current will change the motion of the atoms. Eventually this leads to the effect of electron migration, where the current will make the atoms move in the system, and which eventually can make things break down. I think this is due to the battery, but anyways, it's an important effect. And if you talk about thermoelectric specifically, you can have drag effects between the electrons and the phonon flow. So basically, this is systems where the non-equilibrium is very important. But I think in general, when you look at structures and you want to look at devices, these are out of equilibrium. And you are not interested in general for applications in very small temperature differences. You are looking at large non-equilibrium, and you are not looking at, you don't want to look at very small currents. You want to have real device conditions. So this is what we are trying to get at. And this is very challenging. First of all, you have these non-equilibrium electrons, so you need to take this into account in the electronic structure. And we'd like to be able to calculate these current-induced forces and also the joule heating via this non-adiabatic coupling to the phonons. And what I'm trying to push here is this non-equilibrium Green's function method in combination with DFT. And it's very nice that we already had the introductory talk by Alexander Rocha yesterday. So I'm going to lean heavily on this. And then the description of the phonons. The description of the phonons, we're going to use the semiclassical Langevin equation. And I'm going to show how you can populate this equation with parameters from the DFT-NEGF calculations, and basically do, at least in the long run, do calculations where you can predict effects. This equation you can use in the harmonic approximation. That's the derivation we saw from Abhishek Dar yesterday. I'm also going to lean on that in the harmonic approximation, but you could also push it to the anharmonic approximation and just say, okay, I just use the anharmonic forces in the Langevin equation for the dynamics if the anharmonics is small. So if we look at a concrete system like a molecular conductor, and we pass a current there, to describe this even in steady state is tricky. The electrons, they will pump the high frequency vibrations, and these vibrations will then distribute their energy via anharmonic coupling to low energy vibrations. And this is where the vibrations can couple to the typically heavy metallic electrodes and get rid of the heat. So you need to have the coupling to the electrons, and you need to have these anharmonic couplings and the coupling to the electrode, the phonon electrodes, in order to describe this even in steady state. So it's challenging. I'm going to focus a bit on graphene nanostructures for some of the examples, and of course there are many reasons why we can get funding for this, but also it's a very interesting system because you have this very high thermal conductivity and very high electrical conductivity, and very importantly for this is that you have a very high tunability of these properties if you start to do nanostructuring of graphene. So for instance, if you make a neck in graphene, and you can do that with, for instance, e-beam lithography. This could be sort of the simplest generic structure, and this has been done actually down to a single atomic chain. This is one system, but you could think of of systems which consist of these NEGs, for instance, in these nanomeshes or graphene antidot lattices, where you have many of these, a kind of what we saw in the silicon case in the talk yesterday. And one very interesting when it comes to the electronic structure of graphene is that you can tune the Fermi level of graphene quite a lot just by a gate. So compared to metals, where the Fermi level is completely fixed, here you have this high tunability, and you also have that for other 2D materials. So for that purpose, it's very interesting to use. So people are thinking about now using graphene to contact other 2D materials, or even down to single molecules, so you can control the transport with a gate. So these are systems where I will concentrate on the examples. So first topic here, that's the non-equilibrium Green's function DFT method. So I'll be rather brief here, leaning on the lecture by Roger. So the main idea here is that we describe some system, let's say in the simplest case a junction, and then we can include in our calculation the coupling to the semi-infinite leads here via the self-energy trick. And the most important point is that we can adjust the chemical potentials in this left and right electrode. You can fill these up to different levels, and then you have a current, a steady state current running in the system. And you can study what the system and the potential and Hamiltonian looks like in that case. So you're really dealing with a structure which is under operating conditions, where you have the current. And as I said, you can do this with DFT without any fitting parameters. Of course, there's a bunch of approximations that we're using. But okay, in the first place, we can live with that, and then we need to clean that up at a later stage. So just to show and introduce some of the quantities here, you have these kind of Green's functions here, lesser and greater, where these describe the vacant density of states or occupied density of states in the system. And in equilibrium, these are simply related with the Fermi function, but out of equilibrium, they're not. So you need to calculate these. And the way you do that in steady state is that you calculate these self-energies which describe the coupling to the electrodes. You will have one which describes the scattering in to the system from an electrode alpha, and one which scatter out from an electrode alpha. And you assume always in these calculations that these electrodes, these are in equilibrium with their own chemical potential. So these you can calculate from DFT, and these are nothing but scattering rates in and out, these gamma functions. And once you know these Green's functions, when you know, for instance, the occupied density of states, you can integrate that up, and then you get the density matrix in the system, and that's what you need for DFT. That's the main quantity. And of course, this is you need to do self-consistently, because these Green's functions depend on the Hamiltonian, and the density comes from the Hamiltonian, so that you solve self-consistently. And in the end, you can calculate the current, and that is nothing but accounting, because you can have scattering in and out from an electrode alpha. So you just use these rates. So you can scatter into the vacant density of states, or you can scatter out of the occupied density of states. So this is a quite nice formalism, and the beauty of it is that you can do exactly the same for phonons. So you can have basically the same apparatus for phonons. So the implementation we're using in the actual calculation is this Transistor Method. There are many others. Roger was talking about Semiclassical, and there's also some commercial code. So this is sort of quite spreading out this method now. One of the latest extensions to this is to look at, we are going into is to look at multi-electrode. And for instance, we have looked at a system like this that the experimentalists were thinking they could make. They haven't made it yet, but so this is sort of a T-junction between graphenes, and then you can treat this as a free probe system where you have one electrode here, and one here, and then you can calculate the conductance from between each of these electrodes and look, for instance, what happens if I have a different interface structure here, what happens to the transmission and so on. So that's just to show sort of one trend we are taking. So the first example I want to dwell a little bit into is an example where we again look at these constrictions here, and in our calculation we put a gate. So that means we can put in or take out electrons from our constriction here. And I define this parameter G here, which is basically the doping. And in this constriction, if you calculate the electronic transmission in this, you see some resonances, some peaks here, and this is just where the current mainly runs in the center, and here it runs mainly in the edge in this system here. And then when people calculate this for graphene, for instance, for a graphene nanostructure, then they say, okay, I can just put a gate and then I can shift the Fermi level to this resonance and this resonance. And that is partly true, but it's not the whole story, because you actually put in electrons or take out electrons, meaning that you're changing the system. So it's not that simple, and that's seen from this graph here, where we are at 0 bias voltage, and then we change the doping. This is N doping, this is P doping, this is again the transmission, just shifted, and you see this peak here, that's the center peak and the edge peak. I think I've switched the symbols, but never mind. What you can see is that they are shifting with the gating, but they're not shifting like the Fermi energy. This is the Fermi energy, this solid curve here. So it's kind of adding a non-trivial effect to this. It's actually interesting if we then turn on the bias and have a bias of 0.5 volts, so we have different chemical potentials here, then in this case, the resonances actually start to follow more the Fermi level. If we look in the voltage drop, so that is the change in the electronic potential from 0 bias to some bias. So you can think of this sort of as, in a simple way, as the acceleration of the electrons. So where the electrons accelerated, that's where you have the big potential drop. And at 0.5 volts and 0 doping, it's kind of symmetric. It's interesting if you start to do N doping, for instance, then the potential drop is on one side at the positive electrode. And if you P dope, you can switch it to the other side, to the negative electrode. So this is a non-equilibrium effect, this change in the Hamiltonian with bias, and you need to do a calculation to get that out. So you have this kind of selectivity. The reason why you have this is actually quite simple once you've seen it. It's basically that you change the charge inside this constriction. So if it's N-type, then it becomes positive, and that means that the positive electrode is sort of extending into the constriction, and then you have the voltage drop here at the negative electrode, and vice versa for P-type. And the reason for this charging of the graphene neck here, the constriction, can be, or the asymmetry, can be explained by looking at the density of states in the graphene and looking at the charge injected from the left and right electrodes. These are left and right density of states. So it's not to go into this, but it's just to show that you can basically understand this afterwards. So a sort of a side remark on this is that if you want to dope the structure by putting not a gate potential, but putting some dopants, then you can look at the electronic transmission for different types of dopings, acceptor or a donor, for instance, and you can look at it as a function of where you put this dopant. And what we find out is maybe not surprising, but is that you can dope the system by putting these atoms, and you can actually separate the carrier doping and the dopant scattering in such structures. If you put the dopant just outside here, it will still dope the system, but you will not see the scattering because that takes place in the bottleneck here. But if you put the dopant in here, you start to see the scattering. And this we can try to look at. But that was sort of a side remark. Okay, so I want to shift gears a bit and talk about the electron-phonon coupling within the same kind of formalism. And the first point I want to look at is the signals in the current due to the electronic electron-phonon coupling. So the way we do the calculation is that we, inside our calculational box here, where we attach the electrodes, inside here we let some of the atoms move, and that is the atoms where we have the most of the non-equilibriums or in the bottleneck. So yeah, I call it phonons, but it's basically localized vibrations at this point. And then we can make this region bigger in order to converge the calculation. And we can calculate the coupling to the phonons basically from DFT. It's just the derivative of the DFT Hamiltonian with respect to the displacements of the phonons. And we basically that you can transform into this M here, which I will use repeatedly. That's what I'll call the electron-phonon coupling. And all we are going to do now is basically perturbation theory in this M. We're not going to do very high order complicated things. We are just going to do perturbation theory where we expand, we'll call it lowest order expansion. So we take all the quantities that we want to calculate, say the current, and expand to the lowest order in this M, these expressions. And the way we get to the current is within the non-equilibrium Green's functions, sort of, again, kind of easy to understand. We calculate self-energies, but now this time these are scattering rates between states at different energy. So for instance, we will have a scatter in rate to states at energy E due to emission of phonons, so coming from higher energies, or absorption of phonons. So that of course involves the occupied states. Yeah. And we can calculate all these rates, and then in principle you should do a self-consistent calculation if you were to do this better, because of course the occupation of the states depends on the scattering rates, which again depends on the occupations, and you should do this. But that is just summing up a lot of diagrams that you have chosen. So we are not going to do that. We just do a sort of a one-shot calculation. So the specific systems or properties we want to calculate here, that's this inelastic electron transport spectroscopy, tunneling transport spectroscopy. And the nice thing about that is that's a very specific experimental probe where you can see what vibrations will couple to the current and what is the size of this electron vibration coupling. And putting the experiment and theory on top of each other, we can see how well we are doing. So the idea is very simple and goes way back. It's just that you change the bias here, and as soon as you have enough bias so you can excite a vibration, then you see a change in the conductance. So, for instance, in this case, this is the famous gold chain here, which goes way back. This is the differential conductance as a function of bias. And what you see here at this drop here, this is exactly when the current can excite a vibration in here. So you probe the vibration, and typically you take the derivative of the conductance with respect to voltage, and then you see a signal exactly at the phonon frequency. And this is 4 Kelvin, I think. But that can vary. Yeah, I apologize for this slide, but I don't think you will get the. I mean, it was not intended that you should really go into the formulas, anyways. That was why we had this problem in the beginning. So I just tell you in words what this is all about. If you do this lowest order expansion in the electron-phonon coupling, then these signals, the second derivative of the current, you can actually calculate in a quite nice way by having two analytical functions. You can just write them down, and then in front you have some prefactors which can be calculated from all the quantities of DFT that I've just shown you. So you can do a DFT-NEGF calculation, and then you can put it into this formula, and then you get the signals. Okay. And this is a very fast calculation, and okay, I hope it's the only one. But this is what we're doing, and this is an example of such a calculation where we have experiment and calculations for this alkane system on a gold between. This is the system that we looked at yesterday for thermal transport, but this is just electron transport. And here you see the second derivative of the current with respect to voltage, and you see these signals just a few signals, a few selected vibrations, and you can read off what are their energies, and the size of this peak, that's the strength of the electron-phonon coupling. So these kind of systems we're describing reasonably well without any fitting parameters. These days there are coming out experiments where they're looking at these same effects, this inelastic spectroscopy on graphene structures, for instance graphene between hexagonal boron nitride, so a kind of vertical transport, and you see very nice spectra. This is something we're working on at the moment. I will not go much into that. I will go back to this constriction and look at the effect of this electron-phonon coupling when we're passing current here. So we define this as an electron-phonon coupling region. Here we again have the transmission with the resonances. And if you calculate the phonons of this region here, this is the phonon density of states, it's a function of phonon energy, you see a lot of peaks, there's a lot of vibrations in this. But if you calculate this inelastic spectroscopy, the second derivative of the current with respect to voltage, you just see a few, 5, 7-ish. Now, these signals depend critically if you're on resonance or off resonance. You have much bigger signals if you're on resonance and off resonance. So if you gate this structure and do the measurement, this is what is shown in this graph here, then you see signals when you're on resonance and no when you're off resonance. So you can use this to figure out, how far are you from a resonance, and you can of course use these signals here to figure out which phonon vibrations will couple to the electronic current. And if we analyze this, I will not go deeply into that, but for instance, we find that Raman G and D modes, or something which resembles that, is what shows up here. But you also get other modes which couple to the current. There's so far not been an experiment in this. The closest is that people have been able to pick up graphene nanoribbons with the same structure as I'm looking at in the constriction and measure these inelastic signals through this nanoribbon. But this is so far, it hasn't been published because they have not done a very extended study of it. But you find some of these peaks coincide with what we have. But of course, this is a quite different system. So this is to show that this is a very powerful experimental and theoretical technique. Yes. Well, actually, the vibrations that the electron couples to will depend somewhat on the carrier concentration, but this is not the main thing. The main thing, well, this is basically what you see, because what we're changing here is the carrier concentration from on resonance to off resonance, and here we change it continuously. So you see that the size of the signals depend, and to some extent also which signals you see, but okay, I cannot give a good explanation exactly, but of course it has to do with the wavelength of the electrons you are changing, but yeah. Okay, but this is when we are on resonance and we have the strongest signals. Of course, these systems, you have phonons in here, which we are treated as isolated, but of course they're coupling to the reservoirs out here in the graphene leads, and that will broaden it. And then one relevant question is, could you really see these vibrations in spectroscopy because they are really broadened by coupling to these leads here. And here we show the results where we have broadened the vibrations either with this ohmic friction model or with a more accurate imaginary part of the phonon density of states. And you see that they survive. Some survive better than others, so there's another selection rule which comes in due to this. But we think that in such structures this could be a powerful technique. We hope somebody will do the experiments. Let me shift gears to the semi-classical Langevin equation, and here we're going to focus on how the electronic current will influence the phonons, both in terms of how the modes look, but also how they're populated, of course. Yeah. Yes. On this, yeah. Just one way, yes. Mhm. Yes. No, there's no guessing in this. That's the whole point. We calculate it. No. So I come from a technical university. So, I mean, I'm taking the engineering approach. If the electron-phonon coupling is small, you just do a Taylor expansion this. If you have the current, no, it's not put by hand. It's a Taylor expansion. So you take it to the second order in M, and that's your closed expression for the change in current. If M is small, it's fine. You can forget the rest. If M is big, okay, a lot of things can happen, and a lot of things can happen just because of the non-equilibrium and yes, whatnot. Actually, if you just look at M, this is the first order in the derivative with respect to x. Why not have x squared, x to the third? I mean, so we are assuming that we're in the regime where couplings between electrons and phonons are still small. But the point is that you can get quite a lot of effects even in that regime. Mx squared, for instance. Yeah. Yeah, you can. Yeah. Well, it need not be expressed. Okay, that's a more technical discussion. Yeah. No, we're not doing the self-consistent. No, we do perturbation theory. Yes, but even perturbation theory gives you quite a lot. And the question is then, if you want to move beyond, then you are anyway sweeping a lot of stuff under the carpet. So you can do the self-consistent bond, but that's just one series of diagrams. You could think of others. So we're actually, I think we were taking sort of the safe side if we do perturbation theory. When you do perturbation theory, everything is conserved. So then it's also conserved, but then you have to go all the way to self-consistency. Okay, but I apologize for this. So this is just the Langevin equation from yesterday, and for the phonons. So we have one phonon reservoir here, and a harmonic coupling between the reservoir and this central region, and we assume that the coupling is linear, and then we'll have this. Maybe I can write it down. So we have a retarded self-energy. So we'll have a force in the Langevin equation, which will have a retarded self-energy due to the phonons. And then we'll also have a fluctuating force due to the phonons. Now you can do the same trick for the electrons. And you can also, but that is of course approximate, assume that you have something which is anharmonic in here if you want to do molecular dynamics. But let's leave that. You can also treat the electrons as a bath. Then you just add to this a retarded interaction and a fluctuating force coming from the electrons. So the reason why this is retarded is, of course, if you move an atom or move a mode inside this junction, then you will disturb the phonon reservoir, and this disturbance will propagate and hit back on the phonon again inside the junction. So that of course involves sort of the time for propagating in the phonon reservoir. Once we have electron reservoirs, it's a different time scale because the electrons are much faster. But it's the same kind of idea. So what I'm going to describe now is the semi-classical generalized Langevin equation and how you have actually a number of interesting effects in this. You have the Joule heating, you have the forces, and you have other effects because of the current. So coming again back to our model, we treat the vibrations in a harmonic approximation, calculate the vibrations inside our system. We use DFT Hamiltonians to describe it. We calculate also the coupling from DFT. So there's no fitting parameters or putting stuff by hand in what we're doing. Now let me just sketch how it works with coupling these vibrations to an electron reservoir. And I do it in the most pedestrian way. So let's say you have the phonons, the electrons, and the coupling to linear order. And then we just use the equation of motion. I put the mass to 1 and all this. And then we get an equation of motion, which is basically Newton's equation, or it is Newton's equation, except that these x's could be phonon operators. And then we will have this force, then we'll have this force which comes from the electrons. And the idea is now that we'll assume that the electrons are in steady state. So we just have some flowing electrons, and we'll assume that they are so fast, these electrons, so it doesn't matter if you move the atoms a little bit, they will just see the instantaneous position of the atoms. So we will just take this equation and we will average it over these states of the electrons, this steady state current flow. So we'll write it as an average force due to the electrons plus a fluctuating force. And we'll actually take this semi-classical approximation, which in the first place means that x will think of it as a number. So you can think of it as the center of a phonon wave packet. And then we'll treat this as a sort of a normal fluctuating force. And what I'm going to point out is that inside this average force due to the electrons, you will have an energy non-conservative force, you will have friction forces, and you will have some forces which sort of renormalize the vibrations in here due to the current. So this is a deterministic force. And then you will have the fluctuating force, so where the electron current will kick randomly the atoms in the structure. And this will, of course, have some quantum fluctuation, thermal fluctuation, but most importantly, it will depend on bias and include the Joule heating. So the point I'm trying to make in this is that you get something which is kind of intuitive. You get that just the current is hitting the atoms, and you have these average forces. If you calculate in the semi-classical way this force fluctuating correlation function for the electron kicking the atoms, then you get an expression like this where these are the chemical potentials. So you see that the bias goes in there explicitly. And then you have this lambda function here, which I will show several times, and this describes the coupling to the electrons. So this is done in the lowest order in the electron-phonon coupling, which means that this lambda function is second order in the coupling M. If we look at the deterministic forces, these are also given by this lambda function, and essentially this is just what goes into the retarded self-energy of the electron-phonon coupling. If we go to the simple approximation where we assume that the electronic states are in the wideband approximation, so they are not changing with energy, then we can get simple derivations here, and for instance we can split it up into different parts, this expression here, and then you get the electronic friction, which is nothing but some constant times the velocity in this kind of ohmic description. You get also this non-conservative force, which I'll come back to. And then you get a renormalization of the dynamical matrix because of the current-induced forces. And then you get a force which is sort of a little bit exotic. We call it the Barry phase force. It's like a Lorentz force that will act on the atoms due to the current. And it basically will, like a Lorentz force, it will not give energy into the phonon modes, but it will change the way the phonon modes behave. In the wide band approximation, this is 0, so you need some more exotic structure. So just to sum up, what we are assuming is that the electrons are unperturbed by the phonons in the system, so they're just in steady state. And then to lowest order, we see how the phonons are perturbed by the electronic current going to lowest order in this M. So it's basically, for the experts, this diagram here we calculate out of equilibrium. And then we interpret it in this Langevin picture. So this is basically the equation we have for the Langevin equation, where I'm going to focus on the retarded energy and the fluctuating forces due to the electrons. And as I said, they can be calculated from this lambda function. And it involves the electron-phonon coupling, so it's basically this MAMA here, and then the density of states for the electrons. And this alpha index, that's the electrode. So these are the waves coming from, say, the left electrode, and this is what comes from the right or left. So this is something you can just extract from DFT, and then you are all set to calculate this equation. And you can basically just solve it by Fourier transform, as we saw yesterday. Okay, so now let me talk about current-induced forces. And the idea is very simple. We have now a semi-classical equation of motion, basically Newton's equation with some extra stuff. And then if we look at this deterministic force, which I called non-conservative, what it actually means is that if we have a gradient in the current density, you can think of a balloon in a wind, then you can have that this current can drive motion of the atoms. So this red one, that's sort of the simplest way you can think that here it's pushing the atom, and out here the atom is just going without any force. So this is what Todorov and Dundas called the water wheel effect. So because the flowing of the water, you make the water wheel go, and this is a non-conservative force. In the simplest case, you can think of this motion here. Let's say it's a harmonic motion, you have an x and a y coordinate, then this is the equation you have for the mode. You have two vibrations, one in the x and the y direction, and then you have the friction here. And then in this off diagonal, you have something which is asymmetric, and this is nothing but this non-conservative force that you get. And you also have this Barry force in the simple case. And if you solve this just by making this ansatz, you can figure out what are the frequencies of these modes, and then you can figure out that for certain A, values of A, which are there only when you have the current, then you can have a negative Q factor, which means that the current is now driving the atoms around in some kind of circles. These need not be circles in real space, I'll show you that. This is sort of this kind of water wheel. Now let me just show a couple of experiments where these forces could be at play. This is an experiment where they break a small metallic filament, and then you just have a few atoms in here. And then they use a certain protocol. They ramp up the current in time, and then when something happens in the conductance of this system, they ramp it in the other place. So it's like they're flushing current and more current, and then something happens, and then they flush it in the other way. And in this way, they can actually make this configuration here toggle between two or more metastable states. So the current can sort of kick the atoms from one to another. So this could be one example of these current-induced forces where the direction is very important. It's very well known, and it's a very long story, old story, that if you take, for instance, these atomic chains and you ramp up the voltage, they will break at some voltage. That's the statistics of when they break the full line here, or the full curves, and they break around 1 volt. And this is a DFT calculation of this system here. These are the inverse Q factors, so you can say the damping of the different modes. So at 0 bias, the damping is all positive for all the modes here. But if you turn up the bias, and in this case around 0.7, then one of these modes actually gets a negative damping, which means that now the current is driving this motion. And what it looks like is actually it's a linear combination with complex coefficients of the normal modes. And in real space, in this case, it actually means that the atoms are going around in circles, picking up energy from the current. And it basically means that at this critical voltage here, we'll get a kind of a runaway effect where this will just explode. So this is of the order of these voltages you see when they break. But we cannot say that this is the mechanism which makes them break. We don't have the real smoking gun that it is. And I should say we are not neglecting actually the phonon reservoir, the damping to this, which is very important in this case. But anyways, it goes to say that this is not something with very, very small, necessarily very small effect. We have recently looked at the effect where we include all the coupling to the phonon reservoirs and so on, where we look at this, again, this kind of nano ribbon. And the nice thing about it is that if you strip away some of the hydrogen passivation, then you get some localized vibration at the edge here. And for this system, if we pass a voltage of around 0.5 volts, then we can get several of these runaway modes. And this is seen in the calculated density of states, vibrational density of states. The way we see it in our calculation is that we get a negative density of states. That means that we get a negative damping, so where the current is driving the atomic motion. So we predict that you can have actually several of these. And in one case here, you can have that the atoms are actually moving around in real space, but you could also have that they are moving along a line, so you have sort of a push-pull motion where they are driven. So the important point in this effect is that you need at least 2 phonon modes to have this kind of water wheel. So of course experiments in this field is tricky, but the nice thing about graphene is in principle you can, in a transmission electron microscope, you can actually see what goes on almost on the atomic scale when you pass a current. And this is just one example which shows several layers of graphene. Maybe not so easy to see, but you have a kink here at the edge which is actually moving by the current. And it's at this point it's assumed that it's actually these dimers which are flying off. So maybe you see the effect there. Okay, so I'll switch gears a little bit and talk about another way that these current-induced forces manifest themselves. And that is in the excess heat distribution. So this is one experiment. I guess these are very, very difficult to make, but at least it has been possible to go a little bit in that direction. So here they have again this kind of atomic scale junction, and then they pass a current. And what you see here are thermometers. So they are able to measure out in the electrodes how much the phonons are heating up. And most of the energy is released by the current in here where you really have a few atoms. So you see how this excess heat is moving. And what they see in this experiment is that one electrode here is heating up more than the other. So they put a picture like this, that there's like a hot spot where the phonons are heating up, and it's going with the electron flow. Of course, this could mean that you had some structure which is asymmetric inside here. But when they change, they can, for the same structure, change the electron flow from one direction to the other, and they see this hot spot is moving along the electrons. So it could be some kind of a drag effect, that you drag the heat along with the current. Now we have more recently derived this, again, lowest order perturbation theory for now how this is the phonon heat current. And you can write it out in these kind of Landor-ish expressions. What I want to point out that now that you just have the phonon Green's functions here, you have the coupling, the gamma for the coupling to the phonon bath, and you have again these lambda functions. So now here I look at the heat current under a bias of as a function of bias in the system, and this is at 300 Kelvin, and of course then the electrons will kick the atoms in here and give some Joule heating, which will flow into these electrodes. But the point is that if I only have the current, the fluctuating force, only have the Joule heating, then it's the same energy flow in this symmetric structure to the left and the right. That's this dashed lines, red and black. But if I include the current-induced forces, then we get a different heat flow to the left and to the right. Now, this is another way to put it here. This is at 1 volt bias. What you see here, that's the kinetic energy, the excess kinetic energy of the atoms, how it's distributed. And up here in the upper panel, that's when we only have the fluctuating forces. And down here we have included the current-induced forces, these kind of water wheel forces. And what we see here is that in this case, I cannot see the red dot, I'm sorry. So you see that the heating, when we include the current-induced forces, is more in one side or the other side. Now that depends actually if the Fermi energy, on the position of the Fermi energy. And of course, when you have big metals like this, you cannot just change the Fermi energy. You cannot dope a metal. But we can, in the calculation, do it by hand, and we can see how the heating changed from one side to the other side when we change the Fermi energy. So you can think of it as we change from electron transport to hole transport, and that changes this distribution. We have done the same for this structure where we have these dimers without hydrogen, and there we can see the same kind of effect, that the heating changed from the dimers on one side to the dimers on the other side, depending on the position of the Fermi energy. And actually, for such systems where you have graphene, you could change the Fermi energy with a gate. So you could maybe look at these effects. So what is the simple explanation? And it is actually quite simple. So if you have a tight binding chain for the electrons, and you have just nearest neighbor springs for the phonons, and then let's say we have, this is our system region where we include the electron-phonon coupling. Oh, sorry. Then let's say we have a current where electrons are moving in this direction, and we have an electron-like band. Then there's a different matrix element for exciting an electron, a phonon in this direction compared to that direction, and that's this difference we have here. So in the end, when I have a very long central system, this is momentum conservation. But even for a small system, you have a reminiscence of this, a difference in exciting a phonon, a different matrix element for exciting a phonon in that direction or that. So if an electron is moving in this direction with a positive momentum, then it will excite a phonon like this when it backscatters. Okay? So the phonon is going that direction. Now if I change the Fermi energy, so I change from an electron-like band to a hole-like band, then the electron is moving this direction, same current as before, but the momentum is in the opposite direction because it's crystal momentum. And when I backscatter the electron, then the phonon is actually the scattered phonon that has the momentum, carries the momentum of the change in electron momentum, and will move in the opposite direction. So this current-induced forces is sort of also what you intuitively can say, it's just a matter of momentum exchange between the electron and phonon system. We have looked a little bit more into this recently, and you can think of a system where you have now the two electron reservoirs left and right, and with different chemical potentials, and then you see a different phonon current flow between two phonon reservoirs at equal temperature going from left and right. Of course, you will have some Joule heating in here, and that will have an equal amount of heat flow to these two. But there's kind of a Peltier, you can say, heat flow, which means that you will have a difference in left and right phonon current. And you can do a linear response kind of theory for this and calculate these kind of drag coefficients. And you can write it again. Now it's again these lambda functions that you get. This time this trace is over phonons, so this is phonon density of states. But it's essentially again these lambda functions. these lambda functions that you get, which are basically these mama traces of electrons, and something you can get from DFT. You can also imagine another situation where you have a different temperature in the phonon reservoir, and in that case you can then drag and drive an electron current using the same kind of same formulas. Okay, the last thing I want to discuss is going back to the non-equilibrium electronic structure. Actually, in all this I've shown, we didn't take the bias into account in the Hamiltonian or in the electron-phonon coupling. This is one extra complication, and I'm going to show that in some cases this could be important. The electron-phonon coupling could be bias dependent, and I think maybe this is what goes on in this experiment by Richard Berndt in Kiel, where they look at a C60 molecule in a STM configuration. They have a tip going down here past current, and then they look at the conductance, time resolved. So this is as a function of tip, they move tip closer, and they can see that at some position the conductance flips between two, you can say a low or high contact or out of contact configuration. They don't know, of course, what configuration they have, but this is what they assume. You have like a tunnel configuration and a contact configuration, and it flips here, and this is what you see in time resolved. And then you can look at what is this flipping rate as a function of bias. So what you have up here, that is the current as a function of bias, and that's a simple linear curve. But if you go down here and look at the flipping rate, it actually flips only when you have a positive sample voltage. And why should you have that? Because in the IV characteristic, it doesn't seem that you have any resonances or anything which prefers plus or minus, but you only see flipping at positive voltages. Now we did a calculation of this, and this shows the electronic transmission. It has a resonance. This is the LUMO resonance of the C60. And the different curves here at zero bias, that is when we change the position of the C60. We keep the positions of the electrode, we just shift it slightly. And you see I can change the conductance quite a lot, but the resonance stay in the position. If I go to negative sample voltages, the resonance also stay in position, it just shifts a bit with the chemical potential of the sample, where it's bonded more strongly. But if I go to positive voltages, when I shift the C60 just slightly, the resonance is moving quite a lot. So this means that at positive voltages, there's a very, very strong coupling between the position of the molecule and the electronic structure. So you can sort of translate that into a very strong electron-phonon coupling out of equilibrium at this voltage. And if we look go back to these voltage drops again and look what they look like, these are the two configurations where I just move the C60 by half angstrom. You can call this sort of tunneling because it's closer to the surface. This is contact where it's closer to the tip. If I have a negative bias voltage, this is what the potential difference looks like. This is the sort of the induced dipole, but this is the potential difference. And you see that the voltage drop is just between the tip and the molecule, which is what you would just imagine. But if you go to positive voltages, what happens is when you change the position of the C60 just slightly, the voltage drop can switch from one position, being between the tip and molecule, to between the molecule and sample. So it's really this non-equilibrium electronic structure which at positive bias is really, you can say, unstable. Again, we have these formulas, but we can sort of translate. The idea is just to say, okay, let's say that the phonon, that's the motion of the C60. That's just a single kind of mode, very simple. And then we assume that calculate the electron-phonon coupling. That's basically how how this LUMO level moves with the position of the molecule. And this is, of course, very bias dependent, so we can extract that from our DFT calculation and see very bias dependent. And then we can do a simple heating model where we just have one fitting parameters, which is the coupling of this vibration to the phonons in the tip and electrode, and then we can actually fit the experiments quite nicely. On the other hand, if we're not including this bias-dependent electron-phonon coupling, it's just a even function, so it's not very, yeah. Okay, so let me just give the take-home messages. So I think in many cases it's the working conditions which are really important, especially for applications. And here for nanostructures you can have very high current density, and you need to go beyond linear response. You can have a number of effects, and I have discussed this DFT-NEGF method, which of course are many approximations. We're doing perturbation theory and so on, but we're not having any fitting parameters basically. And then we have linked this with this generalized semi-classical Langevin equation, so we can calculate the parameters in this. And this gives an intuitive interpretation of these current-induced forces in a classical picture, so you can sort of, I mean, the long-term goal of this is to do basically molecular dynamics, where we see what the atoms are doing, putting in these kind of forces. Okay, thank you for your attention and your patience with the formulas.